Hello, class. Well, this is our lecture on curvilinear motion. I sort of introduced this in the last lecture, and I derived centripetal acceleration. And I'm sure you'll remember my derivation of that, but what we ended up finding was that when a particle or vehicle or whatever is going around a curve, that we've got two types of acceleration here. We've got the velocity around that curve. If it's accelerating, that'd be acceleration. But we've got two different types of accelerations at work. Acceleration in the tangential, and then when we're going around the corner, actually, even if this is a constant velocity, I'm saying as we're going around here, we're going to have, as I derived in the last thing, an acceleration inward. And that normal acceleration is usually called centripetal acceleration, and it's directed inward. And of course, the force that's equal and opposite to that acceleration is the force on the body or whatever in the car or on the vehicle or the particle that's going around this direction. We're going to have a force in the opposite direction too. But this acceleration here, v squared over r. And then if I continue to draw this, you could see that I would have like a radius of curvature is what it's called, right? That's my radius of curvature. So if I know what the radius of curvature is, like in an orbit, in a circular orbit around Earth or something like that, I could figure this out, right? So that's my my acceleration. Now, when we're talking about something that is in orbit, that's what I want to talk about. Is let's say that I had something that was in orbit around the Earth. Let's draw the Earth here. Here's the Earth. Yep, I bet you wondered what that was. No, it's not a basketball. It is the Earth. And so let's say that I'm in orbit about the Earth. So I know what my orbit radius is going to be, right? And if I looked at the spaceship or satellite or whatever that was up there, and I did a free body diagram of that, I would see that I have two forces on it. I have a force that's working in, and I have a force that's working out. And of course, that's the force that I'm talking about, the centrifugal force. So centripetal acceleration, but centrifugal force, right? And just like when I'm accelerating in a car, what's the force on the car? The acceleration is forward, but you in the car are pushed back to the back of the car, right? I'm sure everybody realizes that. So the acceleration is this way, but you're pushed that way. The car accelerates this way, but you're pushed backwards. So that's what it is. And anyway, what we've got is we've got two forces here. We've got the gravitational force, and let's say that we're talking about low Earth orbit, so G would still be 9.81 meters per second squared, right? And if we actually get far away from that, we will have to use another thing. In fact, I'm hopeful that we can get to that in this lecture. So we'll see how it goes. All right. Now, the force going out is going to be m times v squared over r. So everyone see what I've got, what's going on there? So if I look at the summation of the forces, this force has to equal this force. So I have to have mg equals mv squared over r. Well, everybody can see that the m's are going to cancel out right off the bat. And so what I end up with is that G equals V squared over R, or V equals the square root G times R, square root of G times R. So if I wanted to find out what the velocity was to stay in that orbit, right, it would be in this low Earth orbit or whatever, it'd be G times R, the gravitational constant times the radius of the orbit, right? This would be the radius of the orbit, and that would be the gravitational constant at that distance from the center of the planet. And what I wanted to do with this is to do an example to sort of show you what it is that I'm using this information from this curvilinear motion derivation that we did in the last part of the last class. So let's say that I am going around Mars, right? I'm going to give you a little information about Mars too. The gravitational attraction on Mars is 10.72 feet per second squared. So we're gonna switch that if we want to, or we can work in feet per second squared. I'm open to that, right? Assuming that we have that the radius of Mars, now the radius of Mars is 2,000 miles. I may work some of these problems out in feet per second and miles and stuff just to give you some familiarity with the British gravitational system and how to, use that and how to switch back and forth between the two. A lot of good, yep, 3.28 meters equals, feet equals 1 meter. 3.28 feet equals 1 meter. Let's never forget that. All right, let's get back to this. Now, we're going to be revolving around Mars at a speed of 20,000 miles per hour. So we're working in things that you can really understand. I mean, when you look at your speedometer in your car, you see miles per hour. And of course, 10.72 feet per second squared happens to be Mars's gravitational constant. And in low Earth orbit, anything up to, a couple thousand miles away, you could say that that's still going to be Mars's gravitational constant. And of course, that's Mars's gravitational constant. And we know that the Earth's gravitational constant is 9.81 meters per second squared, or 32.17 feet per second squared. And how did I get that? I just multiplied 9.81 times 3.28, right? That's how I got it. Of course, Mars is about 1/3 the gravitational constant of the Earth. So we have that, and I'm just going to work with that right now. I'm not going to say that it's changing and get the weight of Mars. We're going to do that with the Earth in a little while to get the geosynchronous orbit around the Earth. But let's just work on this right now. So we know that we're in an orbit around Mars, and our orbital or our tangential velocity is going to be 20,000 miles per hour. We know that the radius of Mars is 2,000 miles. So I want to know two things. I want to know the radius from the center of the Earth, or the center of Mars, to the spaceship. And then I want to know how far it is above the surface. All right, and that should be very easy, shouldn't it? Right. Okay. So first of all, let's look at the 2,000 miles. I'm going to actually do this in the British gravitational system. So let's write that down there. British gravitational unitary system. A little experience with working in that, and really that, of course, is the 32 points. I'll separate this out. There we go. All right. So I think what I'll do is I'll work in feet, because we're working in feet per second squared and everything. So R of Mars equals 10.56 times 10 to the 6 feet. All right. And so that's going to equal R for the radius. And then oh, just a second here. Let me check something. Okay, sorry about that, but yeah, I just wanted to check to make sure that my numbers were right, and they are. So we've got that in feet. Now what I want to do is change this feet per, or miles per hour into feet per second. So V sub t equals 20,000 miles per hour. So let's change that into feet per second. Well, we know that we've got 1 mile is 5,280 feet. And we know that feet per second, so we've got 1 hour is 3,600 seconds. So 20,000 miles per hour is actually 29,400 feet per second. All right, so we have everything in feet per second squared. So everything is in the British gravitational units that we want. We can switch those back to miles, or we can switch them to meters, or whatever we want to do later on. Doesn't really matter. Right now we've got our equation that V squared over R equals G. Well, if that's true, then doesn't V squared over G equal R, right? The orbit, the radius of the orbit that we're going to be at. So V squared, if we work in this, it's going to be 29,400 feet per second, right? Squared. I should put some separator line in there, probably. No. There we go. So, so that's squared, and then divide that by the gravitational constant. And like I say, if we're within 5,000 miles of the surface of Mars, you know, it's not going to really. Well, I shouldn't say 5,000. Let's say 2,000. And in fact, I probably should figure out what it is anyway. We could do it the longer route, but I'm going to do the same thing for Earth in just a second. So instead of using G, I'm going to use the equation for G, Newton's gravitational equation for G, rather than G. So I'm going to do a problem just like that in just a minute. So I'm just going to use G for this problem. And I probably should have changed that down. Instead of 20,000, that should have been about 17,000, but I'm going to leave it where it is for right now. Okay, feet per second squared. All right. And that should give us the orbit at which we're going to be. So 29. I've already done this, but I'm going to do it again on my calculator just to give you guys the chance to do it too. And I get, well, that can't possibly be right. Is that 80? Well, that's not right. 10 point, let me see, 10.72 V squared. And I have V correct. Let me just try that again. Squared divided by All right, just a second. Let me check something. All right, class, I am back, and yes, I did find an error in the problem. Yeah, we would be like 15,000 miles away from Mars, and that would really have put us far outside of what I could have made a rational assumption that 10.72 feet per second squared is still the gravitational constant at 15,000, miles away. Not miles. Yeah, miles. I think. Yeah, something like that, 15,000 miles. So I didn't want to do that. So what I did was I changed it. And as a matter of fact, what we're going to see is that the velocity I've changed it to for an orbit around Mars, which is a perfectly good orbit, by the way. We're going to find out it's about a 600-mile high orbit, is 10,000 miles per hour. Whereas to have an orbital velocity around the Earth would take at least 17,000 miles miles per hour. So anyway, we're going to see that this is more than enough, and that's what I wanted to point out here, although I'll have to do some calculations along the way. So 14,700 squared divided by 10.72 equals an orbit of 20.16 times 10 to the 6 feet. And I know that doesn't seem intuitive to you, so I'm going to divide it by that and give you the miles, and that would be 3,817 miles high. Now that's from the center of the Earth, right? That's from the center of the Earth, of the planet. So what is that above? So that's going to be an orbit 1,817 miles above the surface. Right? So everybody sees how that works. We're just using equations that we've got for curvilinear motion there and for force and everything else. Now, what I wanted to do was I wanted to look at what would be the gravitational, the orbital velocity for Earth, right? The orbital for Earth. Now, this is just an orbital velocity one. This isn't to figure out geosynchronous orbit, which is what I want to do later. I don't know if I'll get to it in this particular lecture, but I want to do that in the next one. This is just a relatively simple equation that I'm going to show you anyway, because if you remember, v squared over r, in fact, I thought I wrote it down. No, I didn't. So let's write that down. So, v squared over r equals g. So really what that tells me is that v equals the square root of g times r, right? Whichever way you want to look at that equation. And so for the orbital velocity of the for the Earth, I've got the square root of the diameter of the Earth. Now we're going to do this in meters per second, so it's going to be 6.37 times 10 to the 6 meters. And that's the radius, remember, not the diameter of the Earth, but the radius of the Earth. And then also in the SI systems, 9.81 meters per second squared, right? So what we want to do is just take the square root of that, and what we end up with is 7,905 meters per second. And do you remember our conversion factor, 2.237? So we know it's going to be about twice that. So that's about 8,000, isn't it? So twice that is 16,000. And then a little more, 1/5. So it's about 17, maybe 18,000. That's what we think we're going to get in miles per hour, right? And in fact, if you do the conversion, you're going to get 17,684 miles per hour. That is the orbital velocity for Earth. And as you can see, the orbital, this is 10,000 miles per hour is actually beyond the orbital velocity for Mars, isn't it? That's right, because we really only have to get about 160 miles above Mars, and there's no atmosphere to speak of. And figure out what low Earth orbit velocity is for Mars. We know what it is for Earth now. What is it for Mars? It's much less, isn't it? It's going to be almost half of what it is for Earth. So I thought that I would point that out to you. What I want to do next is I want to look at well, I'm looking at two problems. Yep, I think I'm going to do let's see what such time we got. Yeah, because we have actually a little more time than that because I paused it. So let's look at the speed of a satellite for geosynchronous orbit. I don't know if I want to take some room there, but this is going to be for geosynchronous orbit. How far out is geosynchronous orbit? You're probably thinking to yourself, what's he talking about, geosynchronous orbit? Of course, geosynchronous orbit is how all cable satellites or whatever, work. They always stay over the same location on the Earth. And so what's happening is as the Earth is turning, right, the Earth is turning and the satellite is turning. So the satellite goes out and comes back at the same speed as the Earth turns. How fast does the Earth turn? Well, let's see. The Earth turns, and we would say that this would be its angular velocity, wouldn't we? We'd say that the Earth turns 360 degrees in 24 hours, right? Except that degrees mean nothing to engineers. Degrees have absolutely no meaning to engineers. So what we have to do is talk in terms of radians, and that's 2 pi radians, right? In 24 hours. And when we speak of angular velocity, right, you think of it as electrical engineers as 2 pi f, but it's still the same units, radians per second. Radians per second, not hours, not radians per hour. So, what you have to ask yourself is how many seconds are there in a day? You know that there's 3,600 seconds in an hour, and there's 24 hours in a day, so that's 86,000. Let's multiply this. Let's just put a conversion factor in here, right? We want to get rid of 24 hours. I should put a day there, really. 24 hours. So 24 hours, I'll do it this way. 24 hours is 86,400 seconds, right? Everybody knows that? I don't know if they do or not. So we're going to get rid of that 24 hours or that one day, and we're going to replace it with seconds. Now we've got radians per second, don't we? So 2 times pi divided by 86,400 gives me 72 times 10 to the minus 6 radians per second. So that's what our angular velocity of our Earth is, right? It goes around, and so does the satellite, doesn't it? The satellite goes around. So, you know, if the Earth is here and the satellite is going around the Earth is here, the satellite's going around the Earth, the same angular velocity as the Earth is going around, right? So the same angular velocity as the Earth. What's the velocity of that? If I'm turning a wheel around, right? If I'm turning a wheel around and I know what the radius is, and I know what the angular velocity is, can't I figure out what the velocity is going to be? Isn't the velocity just equal to the radius times the angular velocity? That's right. That's exactly what it is. If we look at an arc, right, we know that the length of the arc is the angle times the radius, right? So the length of the arc equals the angle times the radius. And of course, that angle is in radians. And this is in radians per second, right? So we know what the tangential velocity of the satellite has to be, don't we? Because if it's going to stay in geosynchronous orbit all the way around, it's got to be traveling as fast as this. So that's going to be omega times r. Whatever this is omega times r. That's going to be my velocity that I've got out there. Okay. Now, if we wanted to make these two things equal, v squared over r equals g. But what does g equal, really? G is Newton's gravitational constant, 6.67 times 10 to the minus 11, right? Times the mass of the Earth divided by the distance between the center of the Earth and the satellite. So forget this. Let's just equate this to this. If I equate this to this, what do I get? Well, we know that V, just a second, let me check something here. Sorry about that, I had to cough. So let's look at V. So we know that that's omega r, so that's omega r squared over r equals g times the mass of the Earth divided by r, right? So I can get rid of some of these r's. Let me just see what I've got here. 7.2, I've got omega. Shouldn't that be? Yeah, that is omega squared. So I can get rid, let me just expand this a little bit and simplify it. So I've got omega squared, sorry, times r squared. Can I cancel that one r out? Can I do that? Excuse me. Because I'll just omega squared r squared over r equals gm mass of the Earth over r. All right. Wasn't that r squared? Where's GMEO over? This shouldn't this be r? That should be r squared. R squared. R squared. It's getting late. I know. And then I'm going to take omega, because this r is going to cancel out with one of these r's. So that just leaves r up there. And then I'm going to take omega from here and put it down on the bottom. And I'm going to take the r squared from here and bring it up to the r. So that's going to give me r cubed. I'll actually write this out. R cubed. Let's put a separator line in here. I'm just about done. R cubed then is going to be g times the mass of the Earth divided by omega squared, right? Or we can say that r is going to be equal to the cube root of g. In fact, why don't I just write it 6.671 times 10 to the minus 11 meters cubed per kilogram second squared times 5.96 times 10 to the 24 kilograms divided by, we already figured this out, there it is, 72 times 10 to the minus 6 radians per second. And that's squared, and take the whole thing to the cube root. All right. R turns out to be 42.2 times 10 to the 6 meters. Now I know that doesn't mean a lot to you, so I actually turned it into miles as well. So it's 26,234 miles. How about that? That's geosynchronous orbit. And you can switch it into kilometers if you want to work in kilometers, that's fine. But I thought that was quite a long lecture, but a good lecture. Covered a lot of curvilinear motion and figuring out a whole variety of different things that are interesting about orbits and everything else. All right, see you in the next lecture.